So, today we will do fuzzy function. Okay. So, this function you know very well, no? Function you know, na? Domain, range, mapping or whatever. Huh? But here we have fuzzy function. Okay. Added one word, fuzzy function. So, as you know, if we have a set A, set B, I have a function. So, I have three things: domain, F, and this codomain. What's range? Okay. So, that means we can have this fuzzy function of three types. Okay. So, one is that I can have this F as crisp. Okay. This function F may be crisp and these A and B may be fuzzy. This is one. Another case may be function F is crisp, here some fuzziness is there, but this is crisp, but its range then will be what? Fuzzy. No, F is crisp, here some fuzziness is there or uncertainty is there. So, if I take F of that, so that introduces fuzziness here, that is second type, and third type is what remained? This is fuzzy. If F is fuzzy, now if F is fuzzy, then if whether A is crisp or whatever, if A is crisp, I take the fuzzified of that, so you will get a fuzzy. Okay. So, in this way three types of fuzzy function are there. So, let me write those and one by one we will discuss. First one is crisp function with fuzzy constant. Crisp function with fuzzy constant. Second one is crisp function which propagates fuzziness of independent variable to dependent variable. And the third one is when the function is itself fuzzy. The function itself is fuzzy. So, that I already discussed. There are three types of fuzzy function. First one is crisp function with fuzzy constant. That means your domain and codomain is having some constant. Okay. That if that is satisfied, then it comes to case 1, type 1. Okay. Crisp function with fuzzy constant. Right. Now, crisp function which propagates fuzziness of independent variable. If you have x left side, so f x will be dependent. So, that fuzziness will propagate to the dependent variable, that is your second. Third is the function itself is fuzzy. Fine. So, let us discuss now the first one, that means crisp function with fuzzy constant. Crisp function with fuzzy constant. Suppose we have two crisp set x and y and a function f, these are all crisp. Okay. If we have fuzzy set A and B in this universal set x and y, and those are fuzzy A and B. Okay. So, if x is having a fuzzy set A bar and y is having a fuzzy set B bar, then we say that, see, crisp function, we have the function as crisp. Now, a function will be A bar to B bar with fuzzy constant. What are the constants? If suppose these are the fuzzy sets, so these have your membership functions. Suppose for this we write mu A bar x, this is mu B bar y, but y is what? It will be f of x. Okay. So, here the membership function is mu a bar x, and here membership function is mu b bar y, where y is f of x. And the constant is that this mu a bar x less than equal to mu b bar f x. So, if this is satisfied, membership function or membership values of this all x in a bar, whatever membership functions are there, if those are less than equal to membership function of that f x, okay, then we say this crisp function with fuzzy constant. Let us take the example. Suppose we have two fuzzy sets. We have two fuzzy sets as a bar is equal to 1.5 and 2.8, and b bar is equal to 2.7 and 4.9, and a function y is equal to f of x, and that is your what? 2x, because you see x is in a bar, okay, and this f is crisp, remember. So, f of x 2x 1 2 2 4. Now, see the conditions here. A bar membership function is 0.5, here b bar membership function is 0.7, which is satisfied. Here also 0.8 less than equal to 0.9. So, we have all mu a bar x less than equal to mu b bar f of x. So, this is the first type of function. Fine? Now, coming to the second type, that is, what was the second type? Where crisp function f that propagates fuzziness of independent variable to dependent variable. What do you understand by this? And you have already studied that. We have crisp function, okay? We have crisp functions, and I am telling that it propagates the fuzziness from the independent variable to dependent variable, okay? So, suppose I take some x in a bar or a, I am not telling it is fuzzy set, but there are some elements which are fuzzy, okay? Suppose I have x which is fuzzy, x bar, and I take a function f to be where what I will get? F of x bar for this element. I have already told, suppose I forget about this x bar etc. There are actually, you can generate b from a using some function. Have you read that earlier? We read extension principle. Extension principle. So, what was the extension principle? There we will have b, fuzzy set b, as how we are getting the membership function there, mu b bar y, if you remember, is equal to what? Supremum of mu a bar x and supremum over x belongs to f inverse y, and if f inverse y is not equal to phi, and otherwise it is 0, that means if f inverse y is phi. This you have read, and I can use this same extension principle for this. Only change will be that what we will have, see, mu in place of b bar, because I will get the range of those uncertain variables, independent variables. These are independent variables in A. Okay. So, I have then mu, what I should write for b bar is in, actually it is the range. So, I can have f of x bar, okay, and in place of y it is okay, is equal to supremum or maximum, whatever, supremum of mu. I will not write a bar, I will write x bar, x, and if f inverse y is not equal to phi, another way is 0, if f inverse y is equal to phi. So, by extension principle, we can propagate the uncertainty of that x to f x bar. Let us take one example, okay, fine. So, this is second type of function, fine. Suppose I have a crisp function, I say it is a crisp function f x as 3x bar plus 1, 3x bar plus 1, where its domain A, I have, suppose in A I have different x, this x actually x bar, I am writing, then I will discuss 0.9, 1 0.8, 2 0.7, 3 0.6, 4 0.5, and range, its range B is your 0, 20. So, in this case you see A are having these elements 0, 1, 2, 3, 4 with membership values 0.9, 0.8, 0.7, 0.6 and 0.5. I have an element x bar, see, this is your x bar which is ambiguous, okay, in A, and I have the function f as crisp which is 3x bar plus 1. So, actually this actually propagate that fuzziness there in B. So, that means I can have the propagated fuzzy set in B as B dash or B bar dash, and because this is your 3x bar plus 1, okay, 3x bar plus 1. So, x bar is 0, so it will be 1 with membership function 0.9 because it is propagating. Then 1 means 4.8, then 7.7, then 10.6 and 13.5. Okay, understood? But this is your ambiguous variable x bar, and we are getting this fuzzy set b bar, understood, using this crisp function, fine. So, this is your second type. Now, third type is important. So, I told the third type here, this other two types, our f is crisp. Our f was crisp in the first type, A and B were fuzzy set. In the second type, f is crisp, here some variables, independent variables are fuzzy, and it is propagating to its range. Okay. Third type, we have actually here two types are there, single fuzzifying function and second is fuzzy bunch of functions. Okay. So, let us do first one, single fuzzifying function. So, this is actually a function which is actually f bar, and this is from the set x to power set of y, which will be a fuzzy set. Okay? If this type of function is there, then it is called single fuzzifying function. Let us take one example. So, you are seeing it is actually function of crisp variable, fuzzifying function of crisp variable or not. So, if I take fuzzifying function, some function which is fuzzy with crisp, it should give fuzzy. Okay? So, consider two crisp sets A is equal to 2, 3, 4 and B is equal to 2, 3, 4, 6, 8, 9, 12. Okay? So, now I have 3 elements here. Remember, so in this case it will be f bar from A to p bar of B. Okay? And suppose I take few elements, so 2, 3, 4, 3 elements are there. So, I will have f bar of 2, I will write, suppose I have B1. This is a power set. Okay? So, one set is B1 bar, just I am taking on my own, you can take others also. So, f bar 3 is equal to B2 bar, f bar 4 is equal to B3 bar. So, I can write this f bar is equal to B1 bar, B2 bar and B3 bar, okay? Because I have taken 3. Now, B1 bar you have different also. Suppose B1 bar, I have B1 bar is for 2, is generated from 2. So, if I take 2 and suppose this is having a membership value 0.5, depends upon problem, and 4, 1, 6, 0.5, this I am giving on my own, okay? These membership values. So, B2 it is generating from 3, fine, 3, 0.5, 6, 1, 9, 0.5 and B3 bar I can have from 4, 0.5, 8, 1 and 12.5. Fine. Now, you see, actually you see this f bar is a mapping, where this 2 belong to where? A, and it gives you, see, 2 in B1 bar with degree 0.5 or possibility 0.5, with possibility 0.5. Now, if I go here for 2 belonging to A, the mapping gives 4 with degree 1. If I come here, it gives 6 in B1 bar with possibility or degree 0.5. Similarly, I can have others. For 3 belong to A, 3 belongs to B2 bar with possibility 0.5, 6 with possibility 1, 9 with possibility 0.5, like that. So, that is why you see, actually it is blurring the image. It is means increasing, na? Fuzziness is coming. So, okay. So, this is your single fuzzifying function. Okay. Let us come then to fuzzy bunch of function. And as you know, what is the meaning of bunch? In a way it is set, okay, fuzzy bunch of functions. So, here we have this f bar x mu fi mu f bar of fi such that x belongs to x. These are the bunch, you see, this is a bar. Suppose this is a fuzzy set, a bar is x comma mu a bar x x belongs to x. Similarly, f bar x mu f bar fi are different functions. That is why it is bunch of functions f1, f2, f3 depends upon I, and I belongs to n, you can write. Okay? This is okay? Fine. So, this again I will take one example and it will be then more clear. So, let us take x is equal to 1, 2, 3 and f bar I have 3 functions in it, f1 0.4, f2 0.7, f3 0.5, and these functions are given. F1 is x, f2 is x square and f3 is x minus 1. Where remember f1, f2, f3 are what? Crisp or fuzzy? These f1, f2, f3 are crisp or fuzzy? Crisp. But this is your fuzzy f bar total. Here it is as I wrote, here see here f1 or x whatever f1 comma mu of this, f2 comma mu of that membership, f3 comma this, and I have in the domain x is equal to 1, 2, 3. Okay? And these are the functions given. Okay? So, for f1 what I can write? F bar 1. For f1 remember x is 1, 2, 3. So, I am writing f1 bar for f1 1 comma 0.4, good, then yes 2 comma yes, someone was telling correct, 2 comma point no 4 0.4, you are understanding, then 3 comma 0.4, correct. Now for f2 bar, tell me now, 1 is 1 and it is 0.7, yes, now you have got it. Then 4 because I have x square, f2 is equal to x square. So, I have 4 and 0.7, good, then 9.7, understood. So, very easy. F3 bar, it is for f3, I have x minus 1, so it will be what? 0 first, 0, 0.5, then 1.5, then 2.7, 0.5 sorry. Okay? So, now you can see, now if I write, so these are for f1, f2, f3, this is clear. Now, if I want to write from here f1 bar 1, what will be that? Yes? 0.4. f1 bar 1, from these it will come. Or you can see it is not f1, if I put it will be confused, f bar 1, f bar 1. So, see f bar is having a bunch f1, f2, f3 bar with bar if you write. So, f bar at 1 are these or not? Means okay, let us write first 3, these 3 or not? So, I can have 1.4, 1.7 and no 0.5, 0.5 or not? This is coming from 1 na, for 1 it is coming na, all this. So you see now we write usually from first the smaller one. So write for 0, 0.5 and among these I have to choose 1. So actually we choose the maximum with maximum membership value. So I have to write 1.7. Okay. Similarly, I can have f bar 2 as, now I can write directly because these will be there. So 1, 2, 4. Okay. 1.5, 2.4, 4.7. Fine. Now f bar 3 will be what? 2.5, 3.4, 9.7. Fine. So what you are seeing by this? F bar is a mapping from X is your crisp set. You are getting fuzzy. Okay. So for 1, okay, you are getting 1, mapping f bar gives 1 with possibility 0.4. You are getting, sorry, this I have to see, 1 with 0.7 and 0 with 0.5, possibility 0.5. Similarly, for 2 in X domain, the domain for domain it was 2. For 2 you are getting 1 with possibility 0.5, 2 with possibility 0.4, 4 with possibility 0.7, similarly 3. Okay, for this problem, if you change all these X, so the homework is you will draw what are F1, F2, F3. Fine. In one plot also you can plot, in one graph, fine, and see what is happening. And there also previous case also you can plot that actually 2 was going to B1 bar, 3 was going to B2 bar, this is single. There if you see there, if I see that to B1 bar, so B1 bar we was having some element, so you will get one is 0.5, other one is 1 and other one is 0.5, like this plot you will get, but here you will get some curve, okay, approximately. Now the last thing for this for today is maximizing and minimizing set and fuzzy sets actually. Okay. So you know maximizing and minimizing? What was that? If I suppose that f is a real valued function first, okay, and this f belongs to some interval, okay, and that interval will be what? For certain x we will get fx, okay. So that fx will belong to certain interval. So what will be the lower and what will be the upper? So you are expert in function analysis, real analysis. Huh? What will be the Rourkela rule for this f? Huh? Inf f, and this is sup f. Not in this range it will vary, na. Whatever f is there, it is real valued. So inf and sup we want. So this is the interval. So you are not thinking about the interval. You know that inf is minimum, sup is, or not? Correct or not? So inf f and sup f. So from here I can define a maximizing fuzzy set. Maximizing fuzzy set. So suppose I say this as m bar, and this will be your x, and always some membership function x, and you can write. So, main thing is, what is this? In all the fuzzy set theory or whatever we have read, what is this? That is our interest. X you know in the domain. Okay. So, what is this? This we define as mu m bar x. This is the maximizing sets membership function, and we define this as f x minus infimum of f x by, now you remember, supremum of f minus infimum of f. Okay? Fine? So, this is called maximizing fuzzy set. So, minimizing will be what? How you find minimizing? Yes, minus of f. I will find maximization or maximizing set minus f. That will be your minimizing set, or not? As you do in operation research also, same thing. Maximization minimization problem, minus of that. Okay? Minimization is maximization of minus f. Suppose I am given one f x like this, 1, 10, and the graph is like this, suppose, and this is your 10 and this is your 20. Okay? I take an element 5, suppose, here, and an element 8 here, and say this is your 15 and this is your, suppose, 18. So, you see here infimum is 10, this is your f x, this is your x. So, infimum is 10, supremum is 20. So, your function is in between that, in this interval, fine. And here suppose I want to have maximizing for this mu m bar 5, I want to find mu m bar 5, 5 is your x as per your definition that we have written, mu m bar by 5. So, then I will have f of that. What is that? 15. It is given in the graph. 15 minus 10 by 20 minus 10. So, what is that? Half. Okay, that is 0.5. Fine. So, if I want to have mu m bar 8, so what we will have? 18 minus 10 by 10. That means 0.8. So, you are understanding how you find? Fine. So, in this way you can find the maximizing and same minimizing minus of that. Now, if I say you that your f x is some function, continuous function, suppose I write f of x is sin x. Find maximizing means find mu m bar of this x. Find this very easily. So, mu m bar x is equal to f x minus inf of f by sup of f minus, or anyway I am writing like this, inf of f, and f of x is your what? Sin x minus infimum of f, infimum of sin x is minus 1, and this is 1 supremum of f minus minus 1. So, you are correct, 1 plus sin x by 2. Similarly, I can have different function and you can have the membership values of those maxima. These are membership values of those functions cos x. I can have same. I mean, same means procedure is same. Okay. So, but the homework again, plot f x equal to sin x, that you know, and plot this and you see what is happening. Understanding? Because if I plot sin x, okay, so it will be what? So, it will be like this, no. So, what will be this 1 plus sin x by 2, that is class 10 problem. Okay. So, you can see how your maximizing function is going. Similarly, for cos x also you can see. So, in the next class we will do integration and differentiation. Okay. Thank you.